Welcome to part 3 of the ESTeem wireless training class. What we're going to do in this section is we're going to continue on with what we started in part 2, which is the system design of the overall network. Just to recap, the network design actually comes in 3 different parts. The first one is a math modeled analysis, where we go in and we verify that the equipment that we're looking to use has the potential or will give us enough bandwidth for the application that we're putting it into. Once that's been completed, we then proceed to the actual on-site testing, which is the site survey. And then the final step is actually going and verifying what we have done through the site survey, actually on the installed hardware, which is the commissioning side of it. So I would review, if you're picking this up, go ahead and go back over part 2 to see how we got to a lot of these conclusions into the site survey. So to start with, the site survey, the idea behind this, what we're trying to do is we are overall developing a test plan for how we want the system to work. What we're trying to do is we're trying to get what the customer's desires are into an actual operating system. We communicate when we start this process. That's where we start with the RF system design as a whole. We go to the customer, find out what they're looking to do, what are their data requirements, what is the hardware they're putting out in there, and from that we're going to gather the site information. Again, we're going to develop what we went in the first part here in the RF design. We're going to develop our system layout. We need to know the distance, the heights, and everything to that to make those calculations. So once we've developed this plan, what this RF site survey is this is actually, we're putting the rubber to the road. We're actually going to go out there and go to the site, physically put these radios at as close to the actual installed hardware as possible and test to see what they do. Because there's a lot of things that are going to come up in the real world that don't show up in a math model analysis. Overhead power lines, buildings, people that are, a housing development that has a ton of different Wi-Fi signals and things in it. These are things that you just cannot calculate for, and that only an on-site managed testing will provide. The next thing is that there's a lot of things that will come up in the real world that unfortunately on the RF design side, we can only make calculations based upon a direct line of sight between the antennas. If the antennas do not have a direct line of sight, you actually have to physically test those locations to see if it'll work. Just because you don't have a line of sight does not mean it will not work. It just is a concern that we can't design and say, we're fairly certain it will work. So if you don't have a line of sight, really, then that's the purpose of conducting this on-site site survey. So when we're developing this test plan, what we're talking about here is these are the elements that we look at when we actually go and do the RF math model portion of it. The next thing is we actually then move on to the on-site radio measurement, because what we're going to do is we're going to conduct the signal strength measurement from each one of these points. We're going to look for the background noise. We're going to actually finalize what our pathways are going to be. Because in a lot of cases, if we find that we are running across a questionable remote location, we don't know if it's going to work the way we want it to or not, we may have to actually add a repeater site in, or we may have to use one of our other radios as a repeater. That is one of the key benefits for our products, is the fact that any one of our remote sites can be used as a repeater for anybody else within the network. So you can develop these very complex networks without necessarily having to add in specific repeater sites. Well, these are the things, or these are the changes that we want to make to the system, so we know that to begin with. We actually want to confirm the results that we did during our RF design calculations. That's really the point of going out and taking those measurements. To do that, we're actually going to the physical site to inspect what those sites look like, and then take a look at the installation information, and then finally take the measurements on what happens in the system. So how is this actually done? What is kind of the procedure that we do? The first thing we do is we basically review all the topographical maps. In a lot of cases in the RF design side, you're going to find immediately that there are remote locations that you're not going to be able to get a direct line of sight to. They're behind a hill or something like this. So you go out there knowing you're going to need a repeater site for several locations. So you can preemptively look and see what's available. Are there water towers in town if it's a municipal application? Or is there a possible line of sight from one of the other remote sites? And then what we do when we get to the site itself, we do what's called this site walk down. The next slide would go into more detail on what that is, but what we're doing there in that case is we're physically going to each one of the sites and seeing what's available for us to not only test, but to find out what we can do to make that system work. The next thing we take a look at is what's called the pre-test preparation. Before we go out and do any kind of field work, the first thing that we'll always do is put together the hardware that we're looking to test with, everything from the power supplies, the radios, the antennas, the cables, if we're taking coax cables. We put those together and make sure that the system is working, laboratory type system. Then when we get out to the field, because the first thing we're going to do is we're going to set up a reference site. Now that reference site usually starts at the master location, because most sites communicate back to one central spot. This reference site, quite honestly, could be moved throughout the day, because your reference site may become a repeater site, and you may have several sites that talk to it. So what you're doing is overall, you're kind of doing the same thing. We're testing the equipment, we're setting up this reference site, then we'll go out to the remote locations, make the test, and ultimately come back with what results should we have. We then put all of this information into a site survey report. Okay? So the way that we do this is we start first with the site layout. Okay? Repeaters is going to tell us what type of antenna types we would need. So we're going to have, when we go out and do these site survey, we make sure we have enough omnidirectional antennas to make the testing that's required for it, the directional antennas for the remote locations, because we've already looked at the topography in the area, so we know the sites that are going to have issues. We know the sites that are going to be the most questionable. So those are the sites that we need to make sure we've got an answer for when we're done. When we talk about a site walk down, we want to be able to physically inspect each one of these locations. What we're looking for is these line of sight, or we see here on the screen, this LOS blockage. What that is that could be anything. It could be a building, could be a tree, could be bushes, could be, a hill, uh, especially when we're dealing with things in the mining or things that are in stacker reclaimer type situations, to where these line of sight blockages, quite honestly, are man-made and they can come up and go down. So we need to make sure we understand what those are going to be before we do any kind of analysis, and make sure that we design for that when we're doing the site testing. The next thing we're going to take a look at is, what do we have as far as mounting structure? What kind of height is that mounting structure going to be able to give us? Do we need to put a tower at specific locations? Can we get away with using, say, a very low cost antenna tower is a telephone pole? Telephone poles are fairly inexpensive. They can get you 30 feet in the air. You put, a piece of conduit off the side of those, and now you're up to 30 feet, and they're only a couple $100 as far as the solution for it. So there are different ways around this, and these are the things that we're going to make note of when we're doing the site survey, so that we put that inside of the site survey report. When the report gets passed along to the customer, it should be more of a design build specification, and not just that this site worked, this site didn't, this was the signal strength. We're trying to provide as much information as we possibly can when we do these site surveys. That's the main purpose behind it. The next thing to consider is the routing of the cable. Now, for the pole mount type of installations that we have on our Horizon series radios, the routing, you have quite a bit of flexibility, because you can move the Ethernet cable almost up to 300 feet on those with very minimal amount of problem with that. The next problem that we run into, though, is the fact that if we're running a coax cable, the best location in the site, we want to also mount the antenna as close as we can to the control cabinet. Let me kind of draw this, what I'm making a reference to. It'll make a little bit more sense. Okay, let's say for my crude drawing here, I'm going to draw a building, okay? And on this building, there is a nice high structure to where we want to mount. Say this is the front of the building here, okay? Say this is the area that we actually want to mount the antenna on top of, because that's going to give us the best height. The problem that we need to think of here, if the control cabinet is at the opposite wall, all the advantage that we have on the height here is lost in having to add the extra coax cable to the system. So there are different solutions we need to come up with. Maybe we find that putting a pole on this side of the system will give us enough height and is close enough to the control cabinet. Another possibility is we add a control cabinet up here on this side and then run, say, an Ethernet cable down into the control hardware. There are different solutions that we can get to this, but we do need to keep in mind that we definitely want to consider what our routing of these feed line cables are going to be. We don't want to just necessarily select the highest point in the area, because all the advantage that we get out of that can easily be lost. The next thing we need to consider are what we'll call environmental considerations. Placing antennas outside of a smokestack, or if we're putting it by the ocean to where it's going to get salt spray, the antennas need to be protected from that. It's not that these are necessarily an issue. We just need to consider those and make note of those, that where the equipment is actually going to finally be installed, do we have a plan for how to get that solved? Continuing from there, the first thing that we do once we go to the site and we have inspected each one of these locations, we're going to start with our reference site. Now, our reference site usually ends up being the master site, at least as the beginning, because from the master site, we try to get as many locations to talk directly to the master site as we possibly can. Not that repeaters are a problem within a network. It's just the more sites that you have talking directly to the main location, the more efficient the communication is going to be. So we try to get those as best as we can. The first thing to consider, and above all, is that when you install an antenna, okay, we want to look at the placement of that antenna as close as we can possibly get to where it's finally going to be installed. We don't want to necessarily install it on the opposite side of the building or out in a clear area away from the building just to make the best test. We actually want to test it as close to where it's going to be installed in the final installation. You just have to work with what you find out in the field. The next thing is that anytime that you make an antenna installation and you're running a coax cable to it, you always want to check the forward reflected power or the standing wave ratio to make sure that something hasn't happened. It's invariably will happen to anybody that's done enough of these site surveys, that you get out there, you set the equipment up, you go out to a remote location, you've got nothing as far as signal goes. You start finding a repeater site, you still have nothing. You go back to the master, start troubleshooting. Sure enough, you find that a cable has, got a bad connector, a bad connection to it. So anytime that an antenna is mounted, the best thing that you can always do is, it's a very quick test. Just check the forward reflected power. It's going to tell you whether or not there's an issue. The next thing we're going to look at from a reference site is we're going to conduct a spectrum analysis. Now, this does actually take a specialized piece of hardware. And what a spectrum analyzer does, it gives you a visual representation of what's happening within that electromagnetic spectrum in the frequency you're operating on. What it shows you is it shows you signal strengths over time, over a frequency. So if you've got a rise in a signal thing, it will show you actually what's physically happening within that area. The idea behind this is we're looking for a spectrum analysis to find a clear channel. We're trying to find a frequency that no other one around that no one around that system, that location is using. Now, in a unlicensed frequency band, such as the 900, the 24, the 58, there may not be a very specific open frequency available. So what you're looking for is the one that has the least number of users or the lowest signal around that area. For a licensed radio system, when you're actually looking for one that you would go out and apply to the FCC and get the license for, you want to make sure that that is absolutely open. There are no other users on there. And when picking or when selecting a frequency of operation, the one that is actually most isolated, the one that is the clearest in that area. Once that's done, you actually want to select what we're looking for as far as frequency. Now, licensing or licensed frequency bands are a little bit easier that way because you can actually go to the FCC website and find out from there what are actually available for that particular application, what users are in that area. And the best part is they really have some very good search tools from that website. You can put in a location by longitude and latitude, and then you can actually say, give me all the transmitters within this frequency band within a 20-mile radius. And it'll actually produce you a report on that. It's very, very helpful. Now, the one thing, and goes back to doing this for many, many years, the one thing that you'll always want to do before you leave your reference site is a quick connection test. Now, depending upon the radio that you're using, this may be as simple as actually turning the radio on, making sure that you've got a status light, making sure that you can ping that location to the type of radio. And in future training classes, we'll get to the specifics of how that's done. But you want to verify that the remote hardware that you're looking to test with can talk to that base radio before going out and testing the remotes. Anybody that does this enough, I guarantee you will be bit with that at least once. Again, you'll be out at that remote location, you still have nothing. You go to the repeater site looking for where you can find it out, you still have no communication. You back to the master, it's not the address you expected it to be. It's on a different channel or a different bandwidth. By going and making this quick connection test, you can verify that you've got a very simple connection link to that master or that reference location before you head out to the remote sites. This is just the only thing I'll stand on my soapbox about as far as site surveys, that you will definitely get bit by that at least once anytime that you do this kind of testing. So where do we start? Which remote site do we go with? Well, we don't necessarily want to proceed to the furthest site within the system, the one that has absolutely no chance of talking to our reference location, because it's pointless. What you want to do is you actually want to proceed to what we consider the most questionable remote site first. The one that when we did our RF analysis had the least signal strength, or the one that doesn't have a good line of sight. The purpose for this is that when you can go out to that remote location, install your test hardware, and see if you can connect to the master. If you can make a simple connection to it, then great, then you can continue on with the testing. If you can't make a simple connection, well, we know now that we're not going to be able to make this link. What you can then do is look for what site you want to use as a repeater to that location, whether it be another remote site or even a standalone repeater. The purpose for this is this will speed up the overall testing procedure dramatically. Because what happens is if you wait until the very last site and do, say, all the close ones first, then you get to this most questionable one, you find out it needs an actual repeater, then you're going back and basically doubling the work, because then you have to put up the site, another reference site at that repeater location, and go back and test that location once again. It will just speed things up dramatically. So once we've done this, we then can essentially install, and again, anytime that you're putting up an antenna that has any kind of coax with it, we want to check the forward reflected power, or we want to test that antenna. If all that looks good, then we can simply do a quick connect. That quick connect will be different depending upon the different radios that we put out there. Say, for example, in the Ethernet radios, a quick connection will be, can I bring up the remote location across an Ethernet bridge? Can I ping that remote radio? In the licensed radios, that will look like there's an actual software command that you type in connect, and it'll actually link up to it. The idea behind this is that if we can't make this very simple, the smallest packet connection, it's kind of pointless to continue on with taking signal strength measurements and all the rest of it, because we're going to need a repeater site somewhere within the network. If all that looks good, we've actually got a simple quick connect. The next thing we want to look at is how much signal do we have to that location. You can actually Measuring the signal strength can be one of many different ways depending upon the radio that we will cover actually in future chapters of the system, the specifics of how that's done by radio. Most of the time, that signal strength, especially in our wireless Ethernet radios, is all reported from the radio itself. You open up the radio's web page, and from there you can actually go into the wireless status, and the radio itself will tell you how much signal it's receiving across that band. On some of the licensed frequencies, the narrow band radios, you can use the radio will tell you that in part of its diagnostics, or you can actually use a spectrum analyzer. The difficult part of taking a spectrum analyzer on a spread spectrum type network is because the signal is actually spread across so many different frequencies, you can't necessarily look at a peak of any one of those and say, okay, that's my signal strength. What that signal strength measurement is the combination of all of those channels together. So the easiest way and really the most accurate way is using the radio itself to tell you how much signal. If you have enough signal for reliable communication, we can then just basically want to put data across this network. Because the data is going to actually tell us how well those two radios are able to process information between each other. Now, the type of testing that you put across there, one of the most efficient means of doing this, especially most of our radios actually have Ethernet interfaces in them. The easiest way to do this is what's called a ping test. And this is a standard TCP/IP function where you would type in ping and then the IP address of the remote radio itself. And the really nice function of that is the fact that what it will do is it sends a test packet to the remote location, and that remote location sends it back. That is actually one transaction. So you're actually seeing the data going not only to the remote, but going from the remote back to your own radio. So it is a very, very reliable test. You can put the ping into run continuous. You can adjust the size of it. We won't get into the specifics of the pings themselves, but there are a lot that you can do with the test. Really what we're doing is that we're verifying the communication is getting between those remotes. Once we have that information, the signal strength, the ping tests, then the heights, everything to it, we can then move on to the next remote site. And we continue doing this until we have it for all the remote locations. I kind of skipped ahead here. The received signal strength, as I mentioned to you, can be done from the peer list is the best way to do it. What you're looking for in our received signal stress is we want to make sure that not only the signal strength is good, but we want to make sure that the data is what's called updated. One of the things that our utility will put out is the fact it not only tells you the signal strength, but the time that it received that last packet. So if it's been over a minute since you've received a packet and we haven't heard anything from it in that time, that previous signal strength is probably not a good means of measurement. We want to make sure it's not only accurate, but it has come in within a certain reasonable amount of time. And as I mentioned to you, the spectrum analyzer really is best for looking at outside noises within the band. We let the radio do the calculations for it. And what we're looking for when we're doing any kind of an Ethernet type based system, we need a minimum of 10 dB fade margin. This again is the same number that we were looking for when we did the RF design. We want to make sure that the equipment test that we put in there has that same 10 dB fade margin. Now, what sites do we test? Well, as we talked about previously, all sites within this network, no matter how complex the network can actually become, it's still a series of point-to-point connections. Whether we're talking from the remote to the master, the remote to a repeater, the repeater to the master, each one of those links within the networks needs to be tested. We need to have valid data and reliable information from each one of those. We can't just skip past one of it and assume that, we've got one remote looks good. We can assume the other remote looks good. The only thing that is any different than this are specialized type of testing to where most of those are in a mobile environment, to where you're either doing a walk around test, to where you're testing, say, the Wi-Fi coverage in a network. You'll walk around and verify that you can communicate to all the areas you go to. It's not necessarily point to point, but the testing remains the same. You're just doing it on a continuous basis. The next thing that we always want to make sure we have is what we call this long-term testing. Now, we try to do this at a minimum of overnight if you can secure the hardware. You don't want to leave the radios and out in an open field with a battery and hope nobody comes along and takes them. What you do is that you want to use this in a secure building to where you can secure the hardware so we can run it overnight. Because again, most of the RF testing that we're going to be doing is during the daytime. It makes the most sense. So we also want to have a picture of what's happening to the wireless communication in the times that we're not doing the testing. Because most of the networks that we put in are running 24 hours a day, 7 days a week. So we need to have an idea of what's happening during those times we're not there also. That's really the key for this overnight polling test. So what should we have when we're done? What are the things that we're going to need? The greatest thing we need to understand is that we have a signal strength, and that signal strength is above our fade margin, a 10 dB minimum for our spread spectrum radios for all locations. Now, one thing that we can consider here is the fact that a lot of times when we're going out and doing the site survey testing, we don't necessarily have the highest gain antenna we manufacture or that we can get our hands on. So we may have a lower signal. So for example, if we go out and make a test and we're doing it between fairly low gain antennas, say a 10 dB gain remote antenna, and we're getting only a 3 dB fade margin for what that test is, we know that the final installation is actually going to be using a 23 dB antenna. So we know our fade margin with the installed hardware will be above our minimum there. So it's not necessarily we have to have that data at the test, but that the design based upon the test results we did gets above that 10 dB. I hope that makes sense. The next thing is we also want to make sure that the antenna, we have both the antenna heights and the antenna locations by structure, where it's going to be mounted to. Everything to that is noted because that will be in our site survey report. We also want to put in there information as far as the operating frequency. What is the availability? What other channels are in use? What other users are in that area? Primarily, if we're dealing with a license frequency band, we want to have not only a primary channel, but a secondary channel to be able to give them when they go to license the hardware. And if they, for example, somebody was not using a piece of hardware during the test time, they can then go back and say, okay, yes, I want to, this is a secondary frequency. We want to make sure that we provide that information to the customer. The background noise gives us an idea. We don't want to put it onto a channel that has a tremendous amount of noise. So we use this a lot in the older radios where we had to set the squelch manually. The squelch on all of our radios now is set automatically, but we don't want to set it into an incredibly noisy area, or we at least want to have a solution for that, be it through some type of filtering or line filtering. And we also want to make sure that we have the data transmission test from every site within the system and at least one overnight test to the furthest location. Really, the purpose behind that is we're putting everything into what we call this site survey report. The site survey report not only gives what the test results were, but also a system layout. Which sites are going to be repeaters? Which of those locations are going to be used as a primary repeater? Which of those can be used as a secondary repeater to create a mesh network? We will have all this information provided to the customer. Because what we're trying to get is we're trying to get an accurate bill of material, so that when we do the quotation, everything within the cable lengths, the antenna types, everything is as accurate as we can possibly make it. We're also going to have in there special instructions as far as installations. That's where we go back to the cable routing, that we know where all the cables are going to be routed to. The antennas are going to be at specific heights. For example, if they are near power lines, overhead power lines, that we make sure that we note on there that wherever you mount them, so if it were ever to fall, it'll never touch the power lines. All of this information is going to be in there because we want to make sure that we put any kind of safety concerns about the installation within this report. We also want to make sure that our radios, the modem programming commands, are listed within the radio. If they're going to be in a bridge mode, if they're going to be in a router mode, a mobile client, if we know that going into it, we can give them an idea of what this programming is going to look like. The idea also is that, especially in a licensed frequency band, we want to give them a reliable frequency of operation so that they can pass that along to the license itself, so that we can then pass along the site survey report and it becomes a build to diagram. It's not just a report that says, yes, the system will work great. It's exactly how to build it. The customer can then pass that along to a contractor, or as part of an overall contract, the equipment gets purchased and then it gets installed. Then we go on to the last phase of this overall system design, which is what we call the commissioning. Now, the commissioning actually uses the exact same testing procedure that we used during the site survey. The only difference is we're going to be using it on the permanently installed hardware. Really what this does, again, we're looking at the ping tests, verification of the reliable operation, verify that all the equipment within the network has been commissioned, because what we're doing is this will be the backbone for the entire communication network. So any link within our system that has a poor communication link, every device that gets connected to it is also going to have poor communication. So this has to be as reliable as we can possibly make it. Really, another key here of what this commissioning does is this sets the baseline for all future troubleshooting. Where this comes from, coming out of the support side of ESTeem, we will first ask, what is the signal strength that you're receiving between the radios? Well, if you give us a number, say the received signal is a minus 75 dBm, well, that's great. But unfortunately, that number by itself really tells you nothing. The only thing that we can know is that has that number changed from when it was first installed? Or should it be 20 dB greater than that? Or has it lost 20 dB from when it was first installed? Unless you have this baseline information, the signal strength by itself really doesn't tell you much. So the main ingredient that we're getting out of this site commissioning is the ability to go back to it on future troubleshooting to find out where the problem lies. That covers everything that we need to go over as far as the site survey, the site commissioning. The next section that we're going to cover is actually the radios that we manufacture. Where do they fall within this overall radio world that we've kind of painted here? Hope to see you on the next section, and have a great day.